The cosmos holds a perfect sphere of nothingness. This is the Boötes Void, a billion light-year wide shadow in space that should not exist. By the end of this, you will understand why this terrifying emptiness could rewrite the rules of our universe. We are going to explore the evidence for this gaping hole in reality, investigate whether it is a relic from before the Big Bang, and ask if it could be the footprint of something unimaginably large lurking beyond our sight. This is a cosmic detective story, and every clue leads to a deeper mystery. What does true emptiness make you wonder about most? To find this shadow, you first have to see the light. Picture the universe not as a random scattering of stars, but as a grand, intricate structure. It is a cosmic web, a vast network of luminous filaments woven from galaxies and galaxy clusters stretching across the darkness. These filaments are the bright threads of creation, connecting massive nodes where galaxies swarm in their thousands. In the spaces between the threads, you expect to find darkness, pockets of emptiness. But even on the grandest maps of the cosmos, one shadow stands apart. It lies in the direction of the constellation Boötes, the herdsman, and when you zoom out, when you see the full sweep of the luminous web, you see it. A perfect spherical hole, a patch of the sky so dark, so empty, it looks like a mistake. This is the Boötes Void. Its scale is almost impossible to grasp. This sphere of near nothingness is roughly 330 million light-years across. To understand that, think of our own galactic neighborhood, the local group. It contains our Milky Way, Andromeda, and a few dozen smaller galaxies. You could drop our entire local group into the Boötes Void, and it would be like a single grain of sand lost in an empty sports stadium. You could fit thousands of groups like ours inside it with room to spare, and that is what makes it so baffling. According to everything we understand about how the universe evolved after the Big Bang, a void this large should not be here. The cosmic web should not have gaps this wide. The statistics say it is virtually impossible. This is not just a quiet corner of space, it is a profound emptiness. In a region that should be home to thousands of bright galaxies, astronomers have found only about 60. That is not just empty, it is a desert on a continental scale. So the question is not just what is in the void. The real question is, how did this nothingness get there in the first place? The year was 1981, and the universe was about to reveal one of its best-kept secrets. Astronomer Robert Kirshner and his colleagues were not looking for a void. They were simply doing the hard, meticulous work of cosmic cartography using a technique called a redshift survey. By measuring how much the light from distant galaxies was stretched toward the red end of the spectrum, they could calculate how far away each one was. It was like taking a census of the cosmos, plotting each galactic city on a three-dimensional map. Their goal was to understand the large-scale structure of everything. But as the data from one particular patch of sky near the constellation Boötes began to come in, the numbers told a bizarre story. The galaxy counts, which had been steady and predictable, suddenly plummeted. It was as if their map had a giant blank circle drawn right through it. At first, the team assumed it was an error, a glitch in the instruments, a mistake in the calibration, a problem with the telescope. This is the first rule of science. When you find something impossible, you check your work. So they checked and they rechecked. They pointed their instruments again, gathered more data, and analyzed it from every angle. But the result was the same. That shocking drop-off was real. In one direction, the cosmos was full of the expected tapestry of light, but in this other direction, it just stopped. The realization must have been a slow, creeping chill. They had not found a new cluster or a strange galaxy. They had found an absence, a staggering, monumental nothing. The excitement in that moment would have been mixed with profound disbelief. They were looking at a hole in reality itself, a shadow so vast it defied every model of the universe they had. This was not speculation or a fuzzy image. This was hard, repeatable data. The Boötes Void was a fact waiting for the world to understand just how strange it truly was. That discovery forced astronomers to redefine the very idea of emptiness. You see, a cosmic void is not just any patch of dark sky. Scientifically, it is a specific part of the universe's architecture. Think of the cosmos as a vast sea of soap bubbles, where the shimmering walls of each bubble are the brilliant filaments of the cosmic web. Inside each bubble, you find a void. These are the expected empty spaces, the low-density rooms in the grand house of the universe. They are not truly empty, but they are vastly underdense, containing far fewer galaxies than the crowded walls around them. Most voids are a respectable 50 to 150 million light-years across. They are common, and they make sense within our models. They are the bubbles in the foam. But then there is the Boötes Void. It is not a bubble, it is a cavern. At over 300 million light-years wide, it is what astronomers call an ultra-void or a supervoid. The difference is not just one of size, but of essence. Let us look at the numbers. A typical void might have a density about 10% of the cosmic average. The Boötes Void's density is less than 1%. In a region of space that should hold thousands of galaxies, we find mere dozens. That is not just underdense. It is a vacuum on a scale that feels intentional. Then there is its stunning isolation. It is not connected to a network of other voids. It sits alone, a perfect spherical shadow surrounded by the normal, bright web. Its symmetry is another clue. Natural structures in the universe are often lumpy, irregular things. The Boötes Void is remarkably round, as if something carved it out with precise, unimaginable force. So this is not merely a quiet neighborhood. It is a district that was almost entirely abandoned, a ghost town on a continental scale that breaks every rule of cosmic real estate. Its very existence suggests something happened here, something that did not happen anywhere else. Within this immense shadow, a few lonely islands of light stubbornly persist. Calling the Boötes Void completely empty would be a slight exaggeration, but only a slight. Scattered across its billion light-year volume are perhaps 60 galaxies. To grasp how few that is, consider that a similar volume of normal space would contain at least 10,000. Each of these void galaxies is a cosmic castaway, separated from its nearest neighbor by tens of millions of light-years of utter darkness. One of the most famous is a lonely spiral known as MCG plus 0152-002. Imagine our own Milky Way, but instead of being part of a bustling local group, picture it utterly alone, with no large galaxies in sight for 100 million light-years in every direction. That is the existence of a void galaxy. These isolated islands evolve in profound solitude. Without the frequent gravitational encounters and mergers that shape galaxies in crowded clusters, they are often quieter, slower-paced places. They might hold onto their primordial gas longer, forming stars at a more leisurely and steady rate across eons. They are the hermits of the cosmos, living out their long lives in deep silence. But is the space between them truly a vacuum? Not exactly. It is filled with the intergalactic medium, a gas so incredibly diffuse it makes the best vacuum we can create on Earth seem thick as soup. This ultra-thin fog is mostly hydrogen and helium, the leftover raw material from the Big Bang. Within the void, this medium is even more rarefied, stretched to an extreme thinness that borders on pure nothingness. Yet, even here, there is a faint cold glow. This is the cosmic microwave background, the afterglow of the universe's birth. Recent studies suggest this ancient light might be subtly different inside the void. As these photons travel through such an immense underdense region, they can gain a tiny amount of energy, a phenomenon known as the integrated Sachs-Wolf effect. It is as if the shadow itself leaves a faint, cold fingerprint on the oldest light in the universe. So the void is not a perfect nothing. It is a realm of profound isolation, where a handful of lonely galaxies drift in an ocean of near-perfect vacuum, under a sky imprinted with the faintest whisper of creation. It is a landscape of such staggering scale and desolation that it feels less like a place and more like a concept. But this shadow presents a direct challenge to our best understanding of everything. That understanding is packaged in a theory called the lambda cold dark matter model, or lambda CDM for short. It is the reigning champion of cosmology, our most successful and detailed story of how the universe grew from a hot, dense beginning to the cosmic web we see today. The lambda stands for dark energy, the mysterious force accelerating the universe's expansion. Cold dark matter is the invisible, slow-moving scaffolding that gravity used to pull ordinary matter into the structures we see. Run this model on a supercomputer, feed in the initial conditions from the Big Bang, and let it play forward over 13.8 billion years. What you get is stunningly accurate. The simulations produce a universe that looks uncannily like our own, complete with a luminous web of galaxies and clusters, connected by filaments and punctuated by voids. But here is the crucial part. In all those billions of simulated years, in all those virtual universes, you never get a void like the one in Boötes. The voids that form in lambda CDM are smaller, more irregular, and far more numerous. They are the bubbles in the foam, not a single, gaping cavern. This is the core of the mystery, our foundational theory, which explains so much else with remarkable precision, stumbles when faced with this particular shadow. It cannot easily account for an emptiness so vast, so spherical, and so isolated. So we are left with two deeply unsettling possibilities. The first is that we are witnessing a statistical fluke of almost unimaginable rarity. It would mean that in the grand lottery of cosmic structure, our corner of the universe won, or perhaps lost, the most unlikely prize. We just happen to be looking in the exact right direction to see a 1 in a billion anomaly. The second possibility is even more profound. Perhaps the Boötes Void is not a fluke at all, but a sign. A clue written in negative space, telling us that our otherwise successful theory is missing a crucial piece of the puzzle. This impossible shadow forces us to look not just across space, but back to the very first moments of time. To explain the Boötes Void, some cosmologists are turning to a wild chapter in our universe's infancy, a period known as cosmic inflation. Picture the universe not even a second old, a seething, hot quantum foam. Then, triggered by some unknown mechanism, a single, unified field of energy underwent a phase transition. In an unimaginably brief flash, a fraction of a second, space itself expanded faster than the speed of light. It did not just grow, it exploded from subatomic size to something macroscopic, smoothing out the cosmos and planting the tiny seeds that would one day become galaxies. This is the inflationary epoch, and it is a cornerstone of modern cosmology. But what if inflation was not a perfectly smooth, uniform event? What if in that frothing quantum sea, some regions inflated successfully while others did not? This is where the shadow finds a possible home. One compelling idea is that the Boötes Void is a relic, a fossil from that primordial moment. It could be a bubble universe that never quite got going. Imagine our observable universe as one successful bubble in a vast multiverse of such bubbles, all eternally separated by expanding space. The Boötes Void might be our window into a neighboring bubble that stalled, a region where inflation ended too early or never properly began, leaving behind a vast, underdeveloped expanse of near-nothingness within our own bubble. It is a cosmic stillbirth, a ghostly imprint of a universe that almost was, forever embedded within our own. There is another, even more mind-bending possibility. What if the void is not a failed bubble, but a scar from a collision? In the chaotic early moments, two successful inflationary bubbles might have expanded and gently bumped into each other. Where their boundaries met and interacted, the energy could have been dissipated, leaving behind a vast, emptied-out region, a cosmic no-man's land between two separate universes. The stunning spherical symmetry of the Boötes Void fits this idea eerily well, like a contact imprint frozen in spacetime. This transforms the void from a mere curiosity into a potential piece of empirical evidence for the multiverse. It suggests we might be living in a cosmic froth, and this billion light-year shadow is our first glimpse of the foam between the bubbles. The implications are staggering. It means the deepest questions about our own origin, why our universe has its specific properties, why there is something rather than nothing, might be answered by peering into this profound nothingness. The void becomes a looking glass, and what we see reflected is the possibility that everything we know is just one small part of a reality far grander and stranger than we ever dared to dream. The plot, it seems, thickens into a deeper, more unsettling mystery. While the void itself is a study in stillness, astronomers have detected a strange and persistent motion elsewhere in the cosmos, a phenomenon so controversial it bears a name straight from a science fiction novel, the dark flow. It began with meticulous observations of hundreds of massive galaxy clusters. These are the heaviest, most bound structures in the universe, and according to our standard models, their motion should be random, a gentle drift within the cosmic expansion. But the data told a different story. These clusters, scattered across billions of light-years, appeared to be streaming, not expanding outward evenly, but all moving together in a coherent, collective drift toward a single patch of sky near the constellations Centaurus and Vela. It is as if a vast, invisible river is pulling them along. The force required to move such titanic structures would be beyond colossal, and the most shocking implication. The source of this gravitational pull does not appear to be inside our observable universe. It is something beyond the cosmic horizon, a mass so unimaginably large that its gravity reaches across the void to tug at everything we can see. This is where our shadow re-enters the story. Let us connect two impossible dots. We have a billion light-year emptiness in Boötes, a perfect spherical shadow. And we have a mysterious, universal current pulling countless galaxies toward a specific point in space. Could these two be related? One daring hypothesis suggests the Boötes Void is not a failed bubble or a collision scar, but a footprint. Imagine that external mass, that unseen attractor from another realm, passing by or existing adjacent to our cosmic bubble in the distant past. Its gravitational influence would have been like a cosmic plow, sweeping through our region of space and clearing out matter, leaving behind a vast spherical wake of nothingness, the Boötes Void. In this view, the void is not an absence at all. It is the shadow cast by an object of almost inconceivable scale, a relic of its passage. The dark flow, then, would be the ongoing, faint tug from that same external giant, still felt by galaxy clusters today. It is a breathtaking idea. The greatest emptiness we have ever found might be the direct imprint of the greatest mass we cannot see. This transforms the void from a cosmic anomaly into a potential signpost, pointing toward a reality that extends far beyond the limits of our vision. It suggests our universe might be bumping up against something else, something whose gravity writes its signature in both the motion of galaxies and the silence between them. Perhaps the most unsettling possibility is that the shadow is not a natural structure at all. This line of thought leads us away from telescopes and equations and into the realm of pure philosophy, to a question that has haunted thinkers for millennia. What if our reality is not fundamental? The simulation hypothesis, popularized in modern times by figures like Nick Bostrom, proposes a startling idea. Our universe, with all its galaxies, stars, and planets, might be an artificial construct, a simulation running on some unfathomable computer built by a vastly more advanced civilization. If that is true, then every anomaly we find is not a law of physics but a feature of the code. So what does the Boötes Void look like through that lens? In any complex simulation, processing power and memory are finite resources. Rendering a universe of trillions of stars across billions of light-years would be an astronomical computational task, even for a super-advanced programmer. One common trick in video game design is to not render what the player cannot see. Distant landscapes are often low-detail textures or blank voids to save processing power. Could the Boötes Void be exactly that? A vast spherical region of space where the simulation simply did not bother to fill in the details because no one was or is meant to look there. It is a cosmic background texture left intentionally blank to conserve resources, or perhaps it is a glitch, a rounding error in the code that left a sector of the simulation map unpopulated. Its perfect spherical symmetry could hint at a procedural generation algorithm that failed, leaving behind a perfectly empty buffer zone. Maybe it is even a placeholder, a region reserved for future expansion packs in the simulation, still waiting for its galaxies to be installed. This is not science in the traditional sense, but it is a powerful thought experiment that recontextualizes the mystery. The void becomes a potential artifact, a seam in the fabric of our perceived reality. There is another philosophical angle that returns us to the data, known as the argument from cosmic fine-tuning. Physicists have long noted that the fundamental constants of our universe, the strength of gravity, the mass of an electron, the cosmological constant, seem improbably, precisely calibrated to allow for the existence of stars, planets, and life. Alter any one of them by a fraction, and the universe would be a dark, empty void or collapse instantly. The Boötes Void presents a new kind of fine-tuning, but in reverse. Its properties are also oddly precise. Its staggering size pushes right against the statistical limits of our best cosmological model. Its remarkable spherical shape is unnaturally perfect for a random structure. Its extreme isolation is curiously clean. This combination of attributes feels less like a random accident and more like a signature, but a signature of what? Of a natural process we do not yet understand, or of a design choice. The void's existence forces us to confront a profound and unsettling question about the nature of reality itself. Are we studying the laws of a fundamental universe, or are we reverse engineering the rules of a constructed one? Every strange detail, from its impossible scale to its perfect geometry, could be read as a clue. The shadow does not just hide something from our view, it might be inviting us to question everything we assume about the viewer. The shadow in Boötes is not alone. In the direction of the constellation Eridanus, the river, another cosmic abyss has been found. This one, however, was not discovered by counting missing galaxies. It was revealed by a chill in the oldest light in the universe. Embedded within the cosmic microwave background, that faint afterglow from the Big Bang, is a vast, anomalously cold region known as the CMB cold spot. For years, its cause was a puzzle. Was it a statistical fluke in the data, a flaw in our instruments, or something real? Further investigation pointed to a breathtaking culprit. The cold spot appears to be aligned with an immense underdensity in the universe, the Eridanus supervoid. This is a void of staggering scale, possibly even larger than the one in Boötes, stretching over 1 billion light-years. Its discovery method is what makes it so fascinating. While the Boötes Void is a shadow in the light of galaxies, the Eridanus supervoid is a shadow in the light of creation itself. As photons from the cosmic microwave background travel through such an immense, empty region, they lose a tiny amount of energy, creating a subtle, cold imprint on the sky. It is as if the void itself is casting a temperature shadow, so we now have two titanic nothings: the Boötes Void, a near-perfect spherical emptiness defined by a lack of galaxies, and the Eridanus supervoid, a colossal underdensity defined by its chilling effect on primordial light. Their similarities are profound. Both are ultra-voids, regions of such extreme emptiness they strain our cosmological models. Both suggest that the universe can create voids far larger and more extreme than our standard theories predict, but their differences are just as telling. The Boötes void is not as cleanly spherical. Its boundaries are fuzzier, and its connection to the cold spot, while compelling, is still debated by cosmologists. Some argue the cold spot is too large and too cold to be fully explained by even a supervoid of this size. This raises a critical question. Are we looking at two examples of the same rare phenomenon, or at two different cosmic puzzles with different origins? If ultravoids like these are more common than we thought, it forces a major revision of our models. The cosmic web would have far larger holes, and the distribution of matter would be far more uneven than lambda CDM simulations suggest. It would mean the universe is lumpier on the largest scales, hinting at strange initial conditions or unknown forces at play in those first moments. But if their signatures are fundamentally different, it points to a universe capable of creating colossal emptiness in multiple, distinct ways. Perhaps Boötes is a relic of a pre-inflationary bubble, while Boötes is the result of a vast, slow gravitational evacuation over eons. The existence of Boötes transforms the narrative. The Boötes void is no longer a solitary, impossible freak. It is part of a pattern, a member of a mysterious class of structures that exist at the very edge of what we believe is possible. Each one is a data point in a new cosmic mystery. How many more of these billion light-year shadows are waiting to be found, and what will their combined silence tell us about the true shape of reality? But how do you weigh a shadow? To understand what the Boötes void truly is, we need to measure its mass, or rather, its profound lack of it. We need to see gravity's hand at work, even in a place of near nothingness. This brings us to one of astronomy's most powerful tools, gravitational lensing. Imagine space as a vast, flexible sheet. A massive object like a galaxy cluster sits on that sheet, creating a deep dimple. When light from a more distant object travels near this dimple, its path bends like a marble rolling along a curved surface. From our perspective, that distant object's image can be stretched, magnified, or even duplicated. This is Einstein's prediction in action: gravity warping the very fabric of spacetime, and in doing so, distorting the light that passes through it. Now apply this logic to a void. A region with far less matter creates not a dimple but a hill. It is a place of weaker gravity. When light from galaxies far behind the void passes through this underdense region, its path should bend ever so slightly outward. Instead of being focused, the light is subtly defocused. The images of those background galaxies would be minutely stretched in a specific, ring-like pattern around the void's edges. This is an incredibly subtle signal, but if we can detect it, it would give us a direct measurement of the void's total gravitational pull, revealing how much matter, both visible and dark, is actually missing. So astronomers have trained their most sensitive instruments on the Boötes void, searching for this telltale warping in the shapes of millions of distant galaxies. The results, however, are a puzzle wrapped in an enigma. Some studies have found a lensing signal, but it is astonishingly weak. It suggests the void's gravitational shadow is even fainter than expected. This leads to a profound and counterintuitive question. Is the dark matter missing too? In our standard model, dark matter is the invisible skeleton of the cosmos. It forms vast, diffuse halos that envelop galaxies and galaxy clusters, making up the majority of the universe's mass. We assumed that even in a void where luminous galaxies are scarce, dark matter would still be present in a sparse, web-like distribution. But what if the void cleared out everything? What if the process that evacuated the ordinary gas and galaxies also swept away the dark matter, leaving behind a truly pristine vacuum? The faint lensing signal might hint at exactly that, a region where the cosmic scaffolding itself has been dismantled. Alternatively, the dark matter might still be there, but arranged in a bizarre configuration. Perhaps it forms a vast, spherical shell around the emptiness, a hollow halo of invisible mass. This could explain both the extreme emptiness inside and the peculiar, weak lensing at the edges. We are left staring into the shadow, trying to measure the shape of what is not there. The gravitational silence of the Boötes Void is perhaps its most eloquent clue. It whispers that this is not just an absence of light, but an absence of pull, a place where the universe's most dominant ingredient has also gone quiet. This profound isolation does not just create a quiet neighborhood, it forges a unique kind of galaxy. Within the Boötes Void, the few islands of light are not merely lonely, they are fundamentally shaped by their empty surroundings. Think of a galaxy in a crowded cluster. It is constantly jostled by gravitational interactions with its neighbors, its gas stripped away by the hot intracluster medium, its structure warped by close encounters and mergers. It lives a life of cosmic stress and drama. Now place that same galaxy in the heart of the void. Here, the rules are different. For billions of years, these galaxies have floated in serene solitude, free from the gravitational harassment that defines life elsewhere. This extreme environment acts as a time capsule and a laboratory. Without constant disturbances, void galaxies can hold onto their primordial gas for much longer. This reservoir of cool, neutral hydrogen is the raw fuel for star formation. In the deep quiet, star birth might proceed in a slow, steady trickle across cosmic epochs, rather than in violent bursts triggered by collisions. The stellar populations in these galaxies could therefore be older and more uniformly aged, like a forest where all the trees are the same ancient species. They are relics preserving a more undisturbed record of how galaxies grow when left entirely to their own devices. But there is another, more dynamic possibility. That same isolation might also allow for strange and quiet forms of growth. In the bustling filaments of the cosmic web, galaxies often feed on gas streams flowing along those luminous highways. In the void, those highways are gone. Yet, computer simulations suggest void galaxies might still acquire gas through a slower, more diffuse process, gently pulling in the ultra-thin medium that permeates the emptiness. This could lead to a peculiar form of evolution where a galaxy grows not by devouring its neighbors, but by patiently gathering the faintest whispers of matter across eons. Some void galaxies might even exhibit unusual structures like exaggerated spiral arms or lopsided disks, shaped not by external forces but by the gentle, uneven rain of this isolated accretion. This transforms our understanding of the void. It is not a passive whole, a simple absence of things. It is an active and extreme environment that writes its own rules for galactic life. By studying these cosmic hermits, we gain insights we simply cannot get from the crowded cities of the universe. They show us what a galaxy becomes when it is truly left alone. Their pristine state acts as a control experiment, revealing which features of a galaxy are innate and which are imposed by the chaotic environment of the cosmic web. In their deep silence, they hold answers to the most fundamental questions of galactic evolution. The universe is not merely a collection of objects, but a conversation between extremes. To truly understand the shadow of the Boötes Void, you must see the light it stands against. Just as every deep valley has a towering mountain range beside it, the greatest emptiness in the cosmos is mirrored by one of the greatest concentrations of matter we have ever found. This is the Sloan Great Wall, a filament of staggering scale. Discovered in 2003, it is not a wall in the flat, two-dimensional sense, but a colossal river of galaxies, a thick strand of the cosmic web over 1.3 billion light-years long. It is a metropolis of matter, containing tens of thousands of galaxies bound together by gravity in a structure so vast it challenges our very definition of what a structure in the universe can be. And here is the breathtaking part. The Sloan Great Wall and the Boötes Void exist in roughly the same cosmic neighborhood. They are separated by a distance that, on the scale of the observable universe, is relatively small. This creates a staggering duality. On one side, you have the Sloan Great Wall, one of the largest known collections of something. On the other, you have the Boötes Void, the largest known collection of nothing. They are cosmic neighbors, a yin and yang of existence and absence. This pairing is not a coincidence. It is a fundamental feature of the cosmic web. In the early universe, tiny quantum fluctuations were stretched by inflation into seeds of density. Where matter was slightly denser, gravity had a stronger grip, pulling more and more gas and dark matter in over billions of years. This created the great walls and clusters, but for every region that gained, another region lost. As matter flowed into the future filaments and nodes, it drained out of the spaces in between. The voids were not born empty, they were evacuated. The gravitational pull of a forming great wall is like a cosmic vacuum, slowly clearing out the surrounding volumes over eons. In this light, the Boötes Void might be the natural, if extreme, counterpart to the immense Sloan Great Wall. One is the peak, the other is the trough of the same cosmic wave. This relationship suggests a balance, a zero-sum game played on the grandest possible stage. Yet, even this elegant explanation strains under the scale. The Sloan Great Wall is immense, but so are many other filaments. The Boötes Void, however, remains in a class of its own for its emptiness. Does its extreme nature demand an equally extreme cause? Could its vastness mean it was drained not by one great wall, but by several acting in concert over a truly colossal region? Or does its perfect spherical shape hint at a more violent, rapid evacuation than the slow gravitational siphoning we usually envision? The pairing tells us that emptiness and fullness are two sides of the same coin, but the coin we have found in Boötes is oddly, perfectly minted, and it makes you wonder what kind of cosmic mint produced it. Perhaps the void is not a flaw, but a fingerprint from a time before time. To explain a shadow this profound, we must consider a universe with no true beginning and no final end. This is the realm of cyclic cosmology, a radical reimagining of everything. In these models, our universe is not a one-time event, but one link in an endless chain. It expands from a hot, dense state, cools, and structures form just as we see. But instead of fading into eternal darkness or ripping apart, it eventually reverses course. All matter and energy collapse back into an unimaginably dense state, only to rebound in a new Big Bang, starting the cycle over again. The cosmos breathes in and out across eons beyond counting. One particularly elegant version is called conformal cyclic cosmology, proposed by the physicist Roger Penrose. In this view, each cycle or eon stretches on for trillions of years. As one eon ends, all matter decays into massless radiation, and the universe becomes an endless, featureless sea of light. This smooth, infinite state then becomes the seed for the next Big Bang, the starting point for a new eon of matter and structure. But here is where our shadow finds a possible home. The transition between eons is not perfectly clean. Information in some form might bleed through. Penrose suggests that colossal collisions of supermassive black holes from a previous eon could leave imprints on the cosmic microwave background of the next one, as concentric rings of subtle temperature variation. But what if the Boötes Void is an imprint of a different kind? Imagine the end of a prior universe. As that ancient cosmos contracted toward its own big crunch, regions of extreme density and extreme emptiness would have been pressed together. In the chaotic rebound into our current eon, that information might not translate perfectly. A vast region of profound nothingness from the old universe could have been stamped onto the newborn fabric of our own, like a watermark on cosmic paper. The Boötes Void, in this view, is not a structure that formed within our universe. It is a relic, a scar tissue from a cosmos that existed before ours. Its perfect spherical symmetry could hint at the nature of that prior collapse, perhaps marking the boundary of a titanic void that existed in the previous cycle. Its extreme underdensity makes sense if it represents a place where the transfer of information, the translation of radiation back into matter, was incomplete or flawed. This transforms the void from a cosmic anomaly into a potential piece of archaeological evidence. We are not just looking at empty space, we are looking at the fossilized footprint of a universe that died so ours could be born. It suggests our entire cosmic history is just one chapter in an infinite book, and this billion light-year shadow is a sentence carried over from the previous page. The implications are as beautiful as they are humbling. There was no singular creation, only an eternal return. Every galaxy, every star, every atom in our bodies has existed in countless forms across endless cycles. And the greatest emptiness we can see might be the clearest window we have into that infinite past. Gravity is the architect of the cosmos, the force that carves the cosmic web from primordial chaos. But what if we have been reading its blueprint incorrectly? The Boötes Void presents a radical testing ground for this very question. For decades, the dominant solution to many cosmic puzzles has been dark matter, that invisible scaffolding we cannot see but whose gravity we must infer. Yet, a persistent minority of scientists propose a different path. Instead of adding an unseen ingredient, they suggest we modify the recipe itself. This idea is known as modified Newtonian dynamics, or MN. Its core proposition is elegantly simple. Perhaps in regions of extremely weak gravity, like the outskirts of galaxies or the profound emptiness of a void, Newton's and Einstein's laws of gravitation do not apply as we think. A small tweak to the equations might explain the observed motions of stars and galaxies without needing to invoke vast halos of dark matter. It is a classic scientific debate. Do we accept an invisible universe of unknown particles, or do we reconsider the fundamental force we thought we understood? The Boötes Void, with its staggering scale and near-total emptiness, becomes the ultimate laboratory. In our standard model, the void should still contain a sparse web of dark matter. But what if the strange motions we see, or the puzzling weakness of its gravitational lensing signal, are not because dark matter is missing, but because it was never there to begin with? MN proponents argue that in such an extreme low-density environment, the modified laws of gravity would predict a different outcome. The dynamics of the few lonely galaxies drifting in the void, their rotation and their slow paths through the emptiness, could be a direct signature of gravity behaving in a new regime. It is as if the void is a silent room where we can finally hear the faint, true note of gravity, unmuffled by the noisy crowds of matter and hypothetical dark matter halos. If those galaxies move in ways that dark matter models cannot easily explain, but that MN equations predict, the void transforms from a cosmic anomaly into a revolutionary clue. This is not just about explaining one shadow. It is about the rules that govern every galaxy, star, and planet in the sky. The Boötes Void, in its profound stillness, asks us the most profound question physics can face. Are we seeing the effects of something hidden, or are we hearing the true, unadorned voice of the universe's most fundamental force? The silence of the Boötes Void echoes a far more famous silence right here in our own galaxy. For decades, scientists searching for extraterrestrial intelligence have wrestled with the Fermi paradox. The universe is unimaginably old and vast, filled with billions of potentially habitable worlds. The ingredients for life seem to be everywhere, so where is everybody? The question, where is everybody, hangs over every silent radio telescope, every empty patch of sky. One possible answer is as terrifying as the void itself. What if the rise of a truly advanced civilization carries a cosmic cost? Imagine a species that evolves over millions of years, eventually harnessing the total energy output of its galaxy, becoming what we call a Type 3 civilization on the Kardashev scale. Such beings would operate on a level we can barely comprehend, manipulating stars, building structures on a galactic scale. But what if that unimaginable power has a side effect? Or worse, what if it becomes a weapon? The creation of a void like the one in Boötes might be within their capabilities. A civilization seeking to quarantine itself, or to experiment with the fabric of space-time, or even to send a signal of unimaginable scale, might inadvertently or deliberately clear out a billion light-year sphere of galaxies. The void would not be a natural structure but a cosmic engineering project. Alternatively, think of a catastrophic failure, a technology designed to harness dark energy or to create stable wormholes goes horribly wrong, triggering a runaway expansion that evacuates an entire region of space. The Boötes Void, in this dark scenario, is not a fossil from before the Big Bang. It is a scar, a blast zone from a war or an accident that occurred billions of years ago, a silent monument to a civilization that reached for the stars and erased them instead. This transforms the shadow from a natural wonder into a potential artifact. It becomes the ultimate shadow of a giant, a literal shadow cast not by a mass, but by a civilization of gods whose actions write their history on the canvas of the cosmos in negative space. If this is even remotely possible, then the great silence we experience might not be because life is rare. It might be because successful, long-lived civilizations inevitably learn to be invisible, or they leave behind only ruins on a scale we are only beginning to recognize. The void, then, is not an answer to the Fermi paradox, but a chilling new form of the question. Are we alone because life destroys itself, or because it learns to reshape the universe in ways that look to us like nothing at all? That cosmic silence is not just a philosophical puzzle, it is a profound observational challenge. The Boötes Void is so immense, so empty, that simply seeing it clearly is one of the hardest tasks in modern astronomy. The first problem is sheer scale. To map a structure 300 million light-years across, you need a telescope field of view that is both incredibly wide and impossibly deep. You are trying to take a complete three-dimensional census of a billion light-year sphere, but your instruments can only see a tiny fraction of it at a time. It is like trying to map the entire floor of the Pacific Ocean using only a flashlight in a rowboat. You get brilliant, detailed glimpses of small patches, but piecing together the full topography of the abyss is a slow, painstaking process of stitching together countless tiny images. Then there is the problem of emptiness itself. Finding a few dozen galaxies in such a volume is like searching for a handful of fireflies in a darkened cathedral. You need surveys of phenomenal sensitivity, capable of detecting the faintest whispers of light from these lonely islands across unimaginable distances. A single galaxy lost in the noise could skew our entire understanding of the void's structure. This is where our greatest tools come into play. Space telescopes like Hubble and now the James Webb Space Telescope are crucial. By staring at a single patch of sky within the void for days on end, in what are called deep field observations, they gather every possible photon. They can reveal ultra-faint dwarf galaxies that ground-based telescopes would never see, slowly populating the void's true, sparse inventory. Meanwhile, massive ground-based projects like the Sloan Digital Sky Survey have pioneered wide-field mapping. Using a special technique called a redshift survey, they capture the spectra of millions of galaxies, allowing astronomers to plot their positions in 3 dimensions and trace the outlines of the cosmic web and its holes. The future holds even more promise. The Vera C. Rubin Observatory, currently being built in Chile, will begin a 10-year survey of the entire southern sky. Its gigantic mirror and massive camera will essentially make a cosmic movie, detecting changes in the night sky and cataloging billions of galaxies. It will give us our most complete map yet of large-scale structure, potentially revealing new ultra-voids or showing us the Boötes Void in a context we have never seen. All of this work underscores a humbling truth. We are still just scratching the surface of this mystery. Every new instrument, every deeper survey, is like turning up the resolution on a blurry photograph. We know the shadow is there, but its fine details, its true shape, and the exact nature of its few inhabitants are still coming into focus. The void's full story is written in faint light and vast distances, waiting for the next generation of eyes to read it. This colossal absence could not remain confined to scientific journals. The Boötes Void, with its staggering scale and perfect emptiness, has drifted from astrophysics into the very heart of our stories. It has become a powerful icon in science fiction, a ready-made stage for our deepest cosmic anxieties and wonders. In Stephen Baxter's novels Flood and Ark, the void is more than a setting, it is a character. It serves as the ultimate destination for a desperate humanity fleeing a drowned Earth, a place so empty it represents both a final refuge and a terrifying new kind of exile. The journey into that nothingness becomes a metaphor for the unknown future itself. You find its influence in video games and films too, often reimagined as the ghost sector or the Great Silence, a region of space where starships vanish, signals go dead, and ancient, unfathomable phenomena are discovered. It is the perfect blank canvas for narratives about first contact, isolation, and cosmic horror. Why does this specific scientific discovery resonate so powerfully? It taps into a feeling philosophers call the sublime, a mixture of awe and terror when faced with something vastly greater than ourselves. The void is not just big, it is an active negation. It is not a black hole, which is a violent, consuming presence. It is an absence so complete it feels intentional. This makes it the ultimate unknown. Our minds are wired to seek patterns, to fill in blanks. A billion light-year blank is an irresistible provocation. It begs for an explanation, and in the absence of a definitive scientific one, our imagination rushes in. It becomes the footprint of a vanished elder race, the scar of a forgotten war, the egg of a new universe, or the prison of something best left sleeping. The void embodies the core question of all exploration: what lies beyond the map. It is the cosmic equivalent of the old sea charts that warned, "Here be dragons." Only now, the dragons are made of silence and scale. This cultural journey reflects a profound human truth. We use stories to domesticate the terrifying. By placing characters, conflicts, and adventures inside the Boötes Void, we are not diminishing its mystery, we are engaging with it. We are trying on the feeling of being a single spark of consciousness adrift in that immensity, and asking what we would do, what we would become in the face of such absolute stillness. The void's passage into myth proves that some scientific discoveries do more than expand our knowledge, they expand our imagination. They become shared landmarks in our collective psyche, reminding us that the universe is not only stranger than we suppose, but stranger than we can suppose. And sometimes the most compelling story the cosmos tells is written not in stars, but in the shadows between them. The next decade of astronomy will turn its most powerful eyes toward this emptiness, not to fill it, but to listen to its silence. We are moving from discovery to forensic investigation. The first and most critical question is one of basic cartography. Where exactly does the void begin and end? Current maps are like sketches made from a great distance. Future surveys, like those from the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope, will change that. They will not just count galaxies, they will plot the three-dimensional positions of billions of them with exquisite precision. This will let us trace the void's boundary not as a fuzzy estimate, but as a sharp topological feature. Is the wall of galaxies surrounding it sheer and sudden, like a cliff face, or is it a gentle, sloping gradient? The answer will tell us if the void was carved out quickly or slowly, by a violent event or a gradual process. Then we must interrogate the void's few inhabitants. Each lonely galaxy is a witness. By training the James Webb Space Telescope on them, we can read their life stories in infrared light. Their spectral signatures will reveal the precise ages of their stars, the history of their star formation, and the chemical elements in their gas. Are these galaxies truly ancient relics, forming stars at a slow, steady trickle for billions of years, as their isolation suggests? Or do they show signs of a more dramatic past, perhaps a rapid birth followed by a quiet life? Their chemical makeup is a clock. If they are deficient in heavier elements forged in supernova, it would mean they have lived in profound solitude, cut off from the enriched gas flows of the cosmic web. If they show unexpected bursts of youth, it might hint at strange internal dynamics unique to the void environment. These galaxies are not just points of light, they are history books written in atomic lines. We will also search for light where we think there is none. Advanced instruments will scan the void for the faintest, most diffuse glow. This could be the collective light of countless unresolved dwarf galaxies too faint for even our best telescopes to see individually, a hidden population swimming in the dark. Or it could be something more exotic, like a ghostly afterglow from long-dead stars, or even a subtle, uniform radiation signature that points to the void's true nature. Radio telescopes will listen intently, not for alien signals, but for the whisper of cold hydrogen gas. Mapping the distribution of this primordial fuel within the emptiness could reveal if it is truly a clean vacuum, or if it contains vast, invisible reservoirs of raw material in a bizarre state. This ambitious work may one day demand a mission of its own. Imagine a space telescope designed not to look at the brightest objects, but at the darkest patches of sky. A void observer with instruments optimized for extreme low surface brightness astronomy could stare into the Boötes abyss for months, gathering every possible photon. Its sole purpose would be to characterize nothingness. Such a proposal sounds like science fiction, but it is the logical endpoint of our curiosity. Solving a puzzle of this magnitude requires a coordinated, global effort, a shared human project to understand a shadow that has hung in the sky since the first stars ignited. We are building the tools to finally ask the void the right questions, and in its profound silence we may hear the faintest echo of an answer. The simplest answer is often the most unsettling. This void could just be a fluke, a 1 in a trillion cosmic lottery ticket. Let us run the numbers. Our observable universe is staggeringly large, containing perhaps 2 trillion galaxies. Within that vastness, the laws of probability suggest that even the most unlikely events will occur somewhere, given enough space and time. Some cosmologists argue this is all we are seeing. In a cosmos of 2 trillion galaxies, a single region of bizarre emptiness is not just possible, it is statistically inevitable. We just happen to be in the right place at the right time to see it. This is the argument from sheer scale. The universe is so big that the improbable becomes unavoidable. It is like shuffling a deck of cards. The specific order of a thoroughly shuffled deck has never existed before in history. It is a unique, 1 in an unfathomably large number event, yet you hold that unique sequence in your hand right now. Unlikely things happen all the time because there are so many opportunities for them to happen. By this logic, the Boötes Void is simply our universe's version of a perfectly shuffled deck, a random arrangement of matter that looks impossibly ordered but is just a product of vast numbers. This viewpoint wields Occam's razor. Do not invent new physics or multiverses to explain something that random chance on a cosmic scale can already account for. Yet, other scientists look at the same numbers and reach the opposite conclusion. They run sophisticated simulations of cosmic structure formation based on our best models and ask how often a void of this size, shape, and emptiness should appear. The results are stark. In some analyses, the probability of a void like Boötes forming naturally in a lambda cold dark matter universe is less than 1 in a million. Some calculations push that number even lower, into the realm of the infinitesimal. It is not just big, it is too perfectly spherical. It is not just empty, it is too isolated. The combination of its extreme properties, they argue, pushes it far beyond what random fluctuations should produce. This is where the debate turns fierce. One side sees a statistical inevitability, the other sees a statistical impossibility. The core of the disagreement often comes down to what we consider the sample size. Are we judging the probability of this specific void existing anywhere in the universe, which is high, or are we judging the probability of it existing right here where we can see it, which feels astonishingly low? It is the difference between winning the lottery someday and winning the lottery on the very first ticket you buy. The data itself seems to whisper that this is no ordinary emptiness. Its gravitational signature is faint, its borders are clean, its symmetry is unnerving. For many researchers, these details are the fingerprints of something deeper at work. To them, invoking a 1 in a million fluke is not the simplest explanation, it is a surrender. It asks us to accept a staggering coincidence as the answer, when the whole history of science shows that when we find something that breaks the statistical rules, we are usually on the verge of a breakthrough. So we are left with a fundamental choice in how we see the cosmos. Is it a place where anything can happen, making the extraordinary merely rare? Or is it a place governed by strict, knowable rules where an extreme outlier is not a curiosity, but a crack in the foundation, a sign that our map of reality is missing a crucial continent? The shadow does not give us the answer, it only asks the question with the quiet force of 300 million light-years of nothing. The very fabric of space may hold the memory of its own birth. To find the origin of our cosmic shadow, we must journey back to a time before atoms, before light, before even the concept of a particle as we know it. We must enter the realm of the quantum foam. In the first fleeting fractions of a second after the Big Bang, the universe was not a smooth, expanding ball of fire. It was a seething, turbulent sea of pure energy, where the fundamental forces gravity, electromagnetism, and the nuclear forces were unified as one. Space and time themselves were not the stable stage we know today. They were a chaotic, frothing foam, bubbling with virtual particles popping in and out of existence on scales 1 trillion times smaller than an atom. This is the quantum foam, the fundamental texture of reality at its smallest possible scale. As the universe expanded and cooled in those first moments, a cosmic phase transition occurred. Just as water freezes into ice, the unified force began to crystallize, splitting into the distinct forces we observe today. This process, known as symmetry breaking, is believed to have shaped the entire future of the cosmos. But like any freezing process, it may not have been perfectly smooth. When water freezes, bubbles of air can get trapped, creating imperfections in the ice. When glass cools too quickly, internal stresses can create cracks or regions of different density. What if the same thing happened to space-time itself? The Boötes Void could be a fossilized defect from that primordial freezing, a region where the quantum foam solidified with a slightly different structure. Imagine a vast spherical region where the density of the underlying quantum fields is fundamentally lower, like a thinner patch in the cosmic canvas. This defect would have been imprinted when the universe was smaller than a proton, a microscopic flaw in the very geometry of existence. But as the universe inflated to its staggering size, that microscopic flaw was stretched to a macroscopic scale. A quantum crack, a billionth of a meter wide, became a cosmic chasm 300 million light-years across. This idea elegantly connects the largest emptiness we can see to the smallest rules that govern reality. It suggests the void is not an absence of things, but a difference in the foundational substrate of space. The matter and energy we associate with the universe simply never collected there because the ground rules of that region were set to a different value from the very beginning. In this view, the void is not something that happened within the universe. It is a feature woven into the universe's fabric at the moment of its creation, a permanent shadow cast by the way reality itself chose to freeze. That quantum crack stretched across billions of light-years may be more than a passive relic. It could be an engine. The shadow in Boötes does not just sit there, it is actively growing. And its growth is tied to the most mysterious force in the cosmos, dark energy. This is the enigmatic pressure causing the universe's expansion to accelerate, a kind of anti-gravity woven into the fabric of space itself. We usually think of dark energy as a uniform background force, a gentle push that is the same everywhere. But what if it is not? What if the presence, or rather the absence of matter, can change how it behaves? This is where the void becomes a revolutionary laboratory. In a region of such profound emptiness, gravity's pull is almost non-existent. There is very little matter to hold the space together. In this near vacuum, dark energy's repulsive push faces almost no competition. Some cosmological models suggest that within a supervoid, dark energy can operate more effectively, causing the void itself to expand faster than the universe around it. Think of it like a bubble in a rising loaf of bread. The dough around the bubble expands, but the empty space inside the bubble can grow even faster because there is no gluten structure to resist the yeast. The Boötes Void could be that cosmic bubble inflating under its own rules. This turns the void from a static hole into a dynamic entity. It is not merely a place where galaxies are missing. It is a region where the very rules of cosmic evolution are slightly different. The void becomes an amplifier for dark energy, a place where we can see its effects magnified and studied in isolation. But the relationship might be even more intimate. Could the void be influencing dark energy, not just the other way around? Some theoretical work explores the idea that dark energy is not a constant, but a fluid that can clump and vary. A vast underdensity like Boötes might create a kind of dark energy hill, a local fluctuation in this mysterious field. This would mean the force accelerating the universe's expansion is not perfectly smooth. It has ripples, and the void might sit at the peak of one of those ripples, a place where the push is subtly stronger. This positions the Boötes Void at the heart of the universe's ultimate fate. The cosmos is engaged in a grand tug of war. Gravity tries to pull everything together, while dark energy tries to push everything apart. On the scale of galaxy clusters, gravity wins. On the scale of the universe as a whole, dark energy is winning, but in the void, the battlefield is tilted. Here, dark energy operates with little opposition, potentially accelerating the evacuation of matter, making the void even emptier, which in turn could further enhance dark energy's local effect. It is a feedback loop of nothingness. If this is true, then the Boötes Void is not just a curiosity. It is a preview. It shows us what might happen to the entire cosmos in the far, far future, as dark energy continues its work and the universe becomes a colder, emptier, more isolated place. By studying this shadow today, we are not just looking at a fossil from the past, we are peering into the ultimate fate of everything, watching the first act of a cosmic play that will end in eternal silence. That profound silence is an irresistible invitation. When every natural explanation strains at the edges of the impossible, the mind turns to the most profound question of all. Could the Boötes Void be a message, not a natural formation but a deliberate construction, a cosmic signpost left by intelligence on a scale we can barely fathom? This leads to the most speculative search of all, the hunt for an anomalous signal from within the emptiness itself. If this shadow were an artifact, a deliberately cleared zone for some unimaginable purpose, might its creators have left a beacon at its heart? Perhaps the signal is not hidden in the void, but is the void. Its sheer scale and geometric perfection could be the message, a monument so vast it can only be read from a distance of millions of light years. It is a signature written not in light but in the absence of it. Yet, the human instinct is to search for something more direct, a whisper in the radio static. Organizations like the Search for Extraterrestrial Intelligence, or SETI, have long listened to the stars, but their efforts have rarely, if ever, been specifically directed toward the lonely galaxies floating in the Boötes Void. The reason is practical. SETI searches are often piggybacked on other astronomical observations, targeting stars or regions of high scientific interest. The void's galaxies, while fascinating for their isolation, are extremely distant and faint, making them lower priority targets for the precious time on major radio telescopes. Furthermore, the sheer scale of the void works against a simple search. A beacon could be anywhere within that billion light-year sphere. It is like trying to find a single, specific buoy in the middle of the Pacific Ocean by randomly dipping a microphone into the water. The odds are astronomically low, but the very act of considering such a search underscores something profound about this mystery. When faced with an anomaly of this magnitude, a shadow that breaks our best models of cosmic structure, we are compelled to widen the aperture of possibility. We must follow the evidence, no matter how strange the path. Considering an artificial origin is not a surrender to fantasy. It is an exercise in rigorous imagination. It forces us to ask, what would the footprint of a truly advanced civilization look like? It might not be a bustling Dyson sphere or a fleet of starships. It might be a quiet, billion-year-old engineering project on a galactic scale, a restructured piece of the cosmos so permanent it looks like a natural feature of the universe. The silence we detect then is not evidence of absence. It could be a sign of completion. The work is done, the monument is built, and it stands in eternal, perfect stillness, waiting for a species like ours to stumble upon it and wonder. This line of inquiry brings us full circle, back to the human need to find meaning in the dark. The Boötes Void challenges us not just scientifically but philosophically. It asks how far we are willing to let our curiosity roam when the answers defy every expectation. To dismiss the possibility of a signal is to assume we already know all the forms intelligence can take. To listen, even if we hear nothing but the cosmic microwave background and the faint spin of distant hydrogen, is to admit that the universe is still capable of astonishing us. So while no radio telescope is currently trained on the void's heart, the question itself resonates. In our quest to understand this greatest of shadows, we must be brave enough to look for every kind of light, even the kind that has never shone. So many threads lead into this single shadow, a cosmic fluke of staggering rarity, a fossilized bubble from before our universe began, the footprint of an unseen giant tugging at the cosmos, or even a silent monument built by intelligence beyond stars. Each theory illuminates a possible facet of the truth, yet none has fully captured the light. This is the power of a mystery of this scale. It refuses to be solved by a single, tidy answer. Instead, the Boötes Void acts as a cosmic catalyst, forcing us to interrogate the very foundations of what we think we know. It challenges the standard model of cosmology, which cannot easily create such a perfect emptiness. It questions our understanding of dark matter, which seems to whisper only faintly within its borders. It probes the nature of dark energy, which might find its purest expression in that vast nothingness. It even invites us to wonder if reality itself is fundamental, or if we are reading the lines of a deeper code. This billion light-year shadow is more than a hole in space. It is a question mark etched across the sky, a permanent invitation to look deeper and think bigger. In its profound silence, we hear not an answer, but the echo of our own curiosity, reminding us that the universe's greatest wonders are often the ones that defy explanation the longest. Our journey began with a single, baffling blank spot on the map, a quiet patch of sky that, upon closer inspection, revealed itself as a cosmic chasm of impossible scale. We have followed the trail of this shadow from its accidental discovery by astronomers mapping the light, through the lonely galaxies drifting in its vast interior, to the edges of our understanding where physics itself begins to fray. We have weighed it with gravity's own light-bending lens and found its pull curiously faint. We have listened for echoes from before our universe and wondered if its perfect spherical silence is a fossil from a previous cycle of existence. Each theory, from quantum defects stretched to cosmic size to the chilling possibility of a monument built by intelligence beyond stars, paints a different portrait of this nothingness. Yet all circle back to the same core enigma. Is the Boötes Void a shadow cast by something titanic lingering just beyond the curtain of our observable universe? Is it a flaw in the elegant equations of our cosmology, a crack through which we glimpse a deeper layer of reality? Or is it something else entirely, a concept we lack the language, even the physics, to properly describe? This is the enduring power of the shadow. It refuses to be just one thing. It is a question that morphs and grows with every new observation. So tonight, or any clear night, find a moment to step outside. Look up toward the constellation Boötes, the herdsman. To your eyes, it will seem no different from any other patch of starry sky, but now you know, within that apparent emptiness, some 700 million light-years away, lies a sphere of near-nothingness so vast it defies probability. One of the cosmos's deepest secrets is not a brilliant quasar or a swirling galaxy. It is an abyss, a reminder that the universe writes its most profound mysteries not always in the language of light, but often in the eloquent, unsettling grammar of absence. What do you think casts this shadow? Share your wildest theory in the comments below. If journeys to the edges of reality are your kind of exploration, subscribe and stay curious. The next cosmic secret is waiting just beyond the light.